now, and then if you have any question anytime you can ask. Okay, it's better that you unmute and ask. That's much better. So oxidation reaction that we have seen before. I mean, we know that other reactions that we have seen it involves of precipitation or gas evolution or decomposition, displacement or double displacement. All those reactions can be another way we can explain this reaction through oxidation reduction reaction. Oxidation reduction reaction means when there is an electron transfer, okay? When there is electron transfer associated in that reaction, we call it oxidation reduction. If there is no electron transfer, net changes in electron transfer, we will not call it oxidation reduction. It may be placement, it may be something else, precipitation reaction, but there is no net changes or on the oxidation state. All right, so it has to be, for oxidation reduction reaction, it has to be a net oxidation state, oxidation changes on oxidation state. Now for what is oxidation reaction? So when electron, one element is losing electron, then it is called that oxidation is happening there. And another one who is gaining that electron will be reduced. So this is for myself even. So be careful, for sometimes it is confusing because it's very similar term, oxidation reduction reaction, but it's very similar term. So that's why we call, oil and rig. This is a mnemonic that we can remember through by this way. Oxidation is losing, of course, of electron. Losing, it does not have any other thing to lose, only electrons. So oxidation is losing of electron. That means one element, when it is losing electron, oxidation is happening. Rig means reduction is gaining of electron. Now, for example, here, magnesium. When you see magnesium is here, that magnesium is losing of electrons, right? Magnesium is losing of electrons, so oxidation is happening on magnesium here because it's losing of electron. It's not that simple that you think that, okay, yeah, I can see the 4 electrons going out, so it's oxidation. Not that's always simple. So I think please give some equation attention here. So magnesium is losing 4 electrons, and then these electrons, they cannot stay alone. They are negatively charged and very much, should I say, reactive, or they want to be associated with some atoms. All right, so it's just like very unstable thing that will be associated with something, and for this to be associated with, there should be another element or another species who can take up this electron onto them, and that is why oxidation and reduction it happens simultaneously. If there is an oxidation, there must be a reduction as well. So oxidation, half cell, we'll see later on half cell reaction, but this is oxidation, and then this 4 electron is taken up by oxygen, and then oxygen becomes, the reduction happened to oxygen. That means oxygen is gaining the electrons. Okay, so this is quite simple thing, that oxidation is losing of electron, reduction is gaining of electron. But what is the another thing, since we are here already, let me remind you of this thing, that when there is oxidation, we say that there should be a reduction as well. But there are 2 other terms, oxidizing agent and reducing agent. Okay, oxidizing agent and reducing agent. Where good oxidation is happening, it is these 4 electrons, right? It is just like a, how do I say that? It's like a granny, our granny, that she wants to feed you more, that eat some more, like that electrons. So when these electrons is available for someone, this granny is going to feed forcefully to others. So this, which is oxidation is happening, it is a good reducer. Wherever oxidation is happening is a good reducer. Okay, reducing agent. Oxidation, where oxidation is happening is a good reducing agent, and where reduction is happening is a good oxidizing agent, because it is taking up the electron and helping others to be oxidized. And this one is giving electrons to someone and helping others to be reduced. So this is a reducing agent where oxidation is happening, and where reduction is happening is a good oxidizing agent. So this is inverse, right? That's opposite thing. Where oxidation is happening is a good reducing agent, where reduction is happening is a good oxidizing agent. So we need to remember this thing, so our life will be more good, easier. Now, oh, I forgot to turn on my camera here. Hold on. Okay, so now, all right. Yes, I'm here. So you know that robot is not talking with you. Okay, so this is oxidizing and reducing things that we need to know. And this half reaction again is the reaction. We just divide the whole reaction to half. First, where oxidation is happening, we show this one, the oxidation is happening in this part. Another part, we come later on. So it is always easier, right? If we break this big thing in a smaller chunks, or smaller parts, it is easier for us to handle. And same thing goes here. So oxidation reduction is happening. We first want to look at the oxidation state, reaction where oxidation is happening. So half reaction we consider, or we complete first, and then we'll go and look for where the reduction reaction is happening. Okay, and later on we have to make sure that the electrons and all those elements number are same exactly from the both sides. So this is the full reaction, that on both sides number of electrons are same. So there is no extra electron. If there is an extra electron, there is a problem. That means the reaction is not balanced. Probably something else we are missing, or we haven't considered the oxidation state accurately for other elements as well. For oxidation numbers of elements, there is just like other chemistry thing characteristic. It does not have any certain thing, but only few things that we should remember. Hydrogen, we don't consider anyway. Hydrogen does not fit here anyway in the beginning. So first 1 and 2, group 1 and 2, right? Alkali metal and alkali earth metal, they have always 1. This group have always positive 1 oxidation state, and it is fixed. It will never change. Okay, this positive 1. As of now, it will never change. Oxidation state of positive 1. You see, everyone has positive 1. All. And for group 2, that is alkali earth metal, here is positive 2. Always it will be positive 2. It will never change. Right? And another thing that is very certain for all the time, that fluorine has -1 all the time. It will never be impossible that it will be positive or any other oxidation state. It is always negative state. The rest, all of them here, all of them can have a different oxidation state. Even you see this tree, it is not always tree, it can be changed. Depends on the situation, the solvent they are dissolved in, or the medium they are reacting, depends on them. So it will be, this oxidation state can be changed. And for these three, you see, for these three, there is no oxidation state because they are very stable. They are very stable. Helium, impossible that you can take or give an electron to him. Neon as well, it is very stable. Argon also. So only these three. So these three phenomena that we have to remember. That first, this 1A, 2A, their oxidation state is always fixed, +1 and -1. Sorry, +1 and +2. And for fluorine, it is always -1, right? And then for hydrogen, another thing, important thing to remember, hydrogen is positive, always positive, either +1 or -1, depends. It's given actually in the next slide. I hope that you have seen already. So this is the main characteristic of the oxidation state. And this is different from what we have seen the formal charge in the Lewis structure. This is depending on their ability to take or give electrons. Okay, this oxidation state depends on their ability or capability to take or give or donate the electron to others. But for formal charge, it is depends on their charge or their feeling environment. Is it positive mode towards positive, mode towards negative, depends on the availability of the electron towards it. So that is formal charge. It is not the same thing, right? So types of redox reaction. There will be combination, decomposition, single displacement, double displacement. These all things, similar things, precipitation, all those things, similar things that will happen that we have seen in the types of reaction. Not only redox, only the same thing will happen here. This is not something that is we have taken it from the Mars or anything. It is in fact in the chapter of chemistry in reaction, and only the thing that involves or exceptional for redox reaction is their oxidation state will be changed for this reactant to product. When they form in the product, the oxidation state will be changing. There is a rule that I say that here we have to remember that oxidation state, there are some good things to remember, that when it is uncombined state, they are always positive. Sorry, zero. They are always zero. Okay, and for molecules or elements that or ions that have the positive charge on the charge on them, negative charge, positive charge, whatever charge, the oxidation state is equal to them. Okay, the oxidation state for them is equal to that, the charge they are carrying. Okay, and for oxygen, it is most of the time oxygen is -2, but some cases it will be -1 and half. Sometimes it is half. For superoxide, it will be half. We'll see later on. So how do we calculate the oxidation state actually? For example, here is hydrogen and chlorine, right? Hydrogen chloride, maybe hydrochloric acid. So for this case, we know that hydrogen mostly is +1, and I write here hydrogen and chlorine. So hydrogen mostly we know it's +1. And I'm looking for the oxidation state of chlorine. So I do not know what will be the oxidation state of chlorine, right? But I know hydrogen is mostly +1 charge, unless they are with the group 1 or group 2 element. Okay, So if it is group 1, the hydrogen will always be negative. If it is group 1, it will always be negative, but like sodium, potassium, cesium, if hydrogen is with them, then hydrogen is -1. That means hydrogen is taking an electron. But what do you call it? If it is with any other element, hydrogen is +1 charge. So from this postulate or from this information, we put hydrogen is +1 and chlorine we do not know. So we put X. Okay, and we know that total of this oxidation state for a neutral element or neutral molecule, because HCl, when we are writing, we are not showing any charge on it. There is no ion. It's not an ion. It's a neutral molecule. So it will be, the total oxidation state will be 0. And the sum of the oxidation state must be 0, the total one. So what will be the chlorine oxidation state? It should be something negative, right? Because hydrogen is positive, so it should be something negative. And for this case, easy, that hydrogen is +1 and chlorine should be -1, so that it will be equal to 0. Positive plus 1 negative is equal to 0. So in this way, we can find the oxidation state. And there are some things that we should remember. For example, sulfuric acid, we see that here is given actually already. Hydrogen is already +1. We know hydrogen is already +1, but there are 2 hydrogens here, right? There are 2 hydrogens here, so it multiplied by 2. And sulfur, we also know that it is +6, or let's say we do not know sulfur is +6, right? Sulfur, we do not know what's positive or negative or positive. But oxygen, we know that it is -2, and there are 4 oxygen are associated here. 4 oxygen atom associated here, and each of them are carrying 2 negative oxidation state. So +2, 1 times 2 is +2, then -4 times 2 is 8, plus there will be something X that is equal to 0. And if we solve this, we will see that X is equal to +6. X is equal to +6. So this is oxidation state for sulfur in sulfuric acid. This can be different. This oxidation state can be different in other compounds, in other element, and not element, other in other involvement or any other reaction or any other product they are forming. For sulfuric acid, sulfur is +6. And for oxidation state, I mean, it doesn't need to be always. So far, we have seen that it is +1, -1, +2, -2, but it doesn't have to be always that it is an integer. It can be a fraction. Okay, it can be a fraction. For superoxide, HO2 is not H2O. Okay, it's HO2 is superoxide and it's very unstable and it is very oxidizing agent. So this superoxide, you see that it has a negative, half. That is the fraction. The oxidation state is fraction, and because we know that hydrogen can be +1 and oxygen can be -2, right? So oxygen can be negative, must be negative, mostly be -2 oxygen. So to equate this equal to 0, and there are 2, what do you call it, atoms are here. So we know that it is negative. Oh, sorry. What I was going to say is, we know hydrogen is always +1, but oxygen is, what is the oxidation state here? We have to add something that equate is to 0, but there are 2 oxygen atom here. So 2 times half, right? 2 times half, then only it will becomes 1. So for this case, oxygen is negative half. Oxygen is negative half, and then it becomes 0, right? So oxygen is negative half for a superoxide, and by same way, if we calculate, we will find sulfur is positive half, positive 2.5 oxidation state. So anybody can ask the question that how can oxygen can take only half of the electrons, or sulfur can give 2.5 electrons. It is up to your imagination. I mean, this is, there are two electrons. I mean, depends. We also have to see the structure, okay, of that compound, that how they are bonded to each other, and then how they are sharing the electron. One electron is being shared by 2 of the atom, and at the same time, without making a covalent or ionic bond. So this is how it becomes half. That is why it becomes half, but actually there is no half electron, isn't it? Okay, so now if we go to this, any questions so far? I cannot see your screen now, or I cannot see the chat box. If you have a question, please show me your, ask the question. Okay, no question. So now we have to classify the following redox reaction, and this is, it says that for this number A, nitrous acid is decomposed to nitrogen and oxygen gas, and what will be the oxidation state, changes in oxidation state here? So for oxygen, it is -2, right? Oxidation is -2. First of all, this nitrous oxide, this is gas, but this compound is not carrying any charge, so it is neutral. That means it is neutral, so it has to be total oxidation state for nitrogen and oxygen, sum of them should be 0, right? So this is, we know. And oxygen, we always know that it is -2. So what will be for nitrogen? Nitrogen is -1 times 2. If we -1 times 2, because there are 2 nitrogen here, then it will be 0. So from there, we not negative, sorry, +1, yeah, +1 times 2, so it will be 0. So there we see this is +1. The nitrogen is +1, and for this case, nitrogen, what will be the oxidation state for nitrogen here? Anybody? Is given already. So it is a neutral atom for this, right? A molecule. This is a nitrogen, is a gas in the molecule, and this is a neutral. There is no charge here. It's 0 charge. So this is a 0. So this is why oxygen is -2 here, and here as well it is 0. So from here, nitrogen, what happens is it took electron, right? Is it? Nitrogen took electrons and then becomes 0. Can I ask the question? Anybody want to reply? So from +1 to 0, it becomes reduced, right? Oxidation state from +1, it becomes reduced to 0, and oxygen, -2, it becomes 0. That means it increased the oxidation state from negative to towards high from negative. You have to go to 0 first, and then only +1, +2, right? So it's going to higher, so it becomes oxidized. oxygen become oxidized. So in this way, we can find that the oxidation state is changing for all the elements here as well. For lithium, here it is 0. For the second one, the lithium is 0 because oxidation state is 0 here. For nitrogen is also 0 here. But for this case, lithium is positive 1 because remember that lithium is number 1, right? Group 1 element. So the group 1 element is always positive 1. They have always positive 1. So lithium will have positive 1 here times 3, and nitrogen has negative 3 because of positive 3. I mean, it has to be 0, totally 0 because this molecule is neutral. So positive 1 times 3, and nitrogen is negative 3. And this is how it becomes 0. So lithium become reduced, and lithium become oxidized, and nitrogen become reduced here. All right, because they have the oxidation state is changing. Lithium is increasing the oxidation state, nitrogen is reducing, so it becomes reduced. Right. So in this case, we can go for consider all those things, all the reactions. Please go, and I think you haven't. I mean, if you haven't tried, please try. All right. So this reduction oxidation reaction, we can also show or see from the reaction that we also have done it in the lab, that zinc was dissolved in copper sulfate, isn't it? And then you saw that zinc was dissolving somehow, and zinc was dissolving in the solution. So this is an act of oxidation and a reduction reaction. Because of their oxidation activity, their capability to reduce, a reduction, how much it can reduce the others. Based on that, the activity series is created, and from that activity series, we can see that lithium is on top. Right, so lithium has the capability of removing or displacing all of them others, all of them. Lithium has the capability, but copper, those who are at the end or below those activity series, they cannot reduce. They cannot reduce them. They cannot displace them. This is in a very simple sense, that they cannot reduce. All right, so here it says the increasing ease of oxidation, or in another sense, increasing of reducing capability. Reducing capability means they can be oxidized soon or easy. These all elements can be oxidized easily, those who are at the top, and they have much more capability of reducing someone. Right, so the reduction capability increases as we go from bottom to top. And if you can see at the bottom, there are two elements. One is platinum, another one is gold. Gold is AU, actually it is A and U. AU is gold, and platinum. I'm sure that all of us have heard about platinum and gold as well, because these two elements are very precious, we call, and expensive elements. But this is the things that from our the old people, they saw the value of this gold not because you can sell and then you can make a good what do you call it, useful utensil from here, but they saw that gold and these things, it does not rust. It does not get rusted easily. because gold is so inactive, it is at the end of the activity series, it rarely react. It does not react with anyone first. And it also does not get dissolved easily. Right? So because of it, and it is shiny material, so that people kept it for long time and it did not change. It glitter or it last, and its appearance, it does not change. Whereas iron was more important. Iron was more handy thing, more, we use a lot of things. Iron, without iron, we cannot do anything. But the iron is not that expensive because of, first, its availability. Second, it is stability. Its stability is not like that. If you keep iron for some time, it will be rusted, isn't it? So that is the thing, actually. So solution 9 says that aluminium, an active metal that lies above silver in an activity series. So a reaction is expected to occur because aluminium is on the top, right? Aluminium is here. Where is aluminium? Aluminium is here and copper is here. So it's much higher than in the activity series, much on top of it, so that aluminium will replace this silver, and then silver will become solid and aluminium nitrate. By this way, you can also see that this is a displacement, single displacement reaction, and by this way we can see that what do you call it? How do we purify one material, because silver is expensive, more expensive. Aluminium was expensive, more expensive, right? It was before 1880, I think, before 1780, I forgot exactly. Aluminium was very expensive thing because we did not know how to, although aluminium is the most abundant metal on earth, but we, before 1880, we did not know how to purify aluminium from the earth, right? Don't have much time to talk. Okay, so aluminium, and later on we found out aluminium, how to smelt the aluminium, and it's easily. So by this way we can also purify silver from silver nitrate. Okay, so net ionic reaction, only that is involved in ions, is silver nitrate here, because nitrate does not change, right? Nitrate on the both side is on the same, as we have seen before. Nitrate on the both side is in aqueous, so it does not change, and only the silver and aluminium is changing, so they are kept here in ionic reaction equation. Lead as well is hydrogen. Lead is above hydrogen in the activity series, so lead will replace hydrogen, and lead sulfate will. So in our car, in the battery, sometimes we see there are something like fungus or something like that. This is not fungus. This is it's called something, I forgot, the lead salt, maybe, yeah. So this is a lead sulfate, because in our battery there are sulfuric acid is there, so lead sulfate, it falls. Okay, so balancing oxidation reduction reaction. How do we balance an oxidation reduction? As we said, that half reaction method, just break it to half. First, identify where there is oxidation is happening, where the reduction is happening. So oxidation is half reaction, reduction is another half reaction, and then later on we'll combine both together. For example, manganate ion and iron ion, ferrous, in fact, ferrous means 2, right? Ferrous ion is reacting. This is the net ionic reaction. We only know. We do not know what was there, whether it was a potassium permanganate or sodium or whatever was there, we did not know. And iron, it can be iron chloride, iron oxide. We do not know. It's just a net reaction is given. And then this is the product of the reaction. So oxidation, all right, oxidation reaction, where there is electron is being donated, electron is liberated, oxidation is losing of electron. Iron, we see from here to there, it was 2, It was 2, it becomes to 3. So oxidation number is increasing, and that is why oxidation is happening for this iron. All right. For reduction, of course, the rest of the thing reduction will happen. We don't have to think much, but the reduction will be happen. But again, if we want to analyze how really is reduction happening or something else, somewhere else the electron is lost, how do you find it? First, what will be the oxidation state of manganese here on the reactant side, right? We do not know. Let's say it is positive X. And oxygen always negative, since there is no group 1, group 2. So oxidation, oxygen, actually it is group 2. So mostly probably positive 2 it will be, but let's just calculate it. So oxygen will be positive negative 2, because oxygen mostly negative 2 times 4. Times 4, and it is equal to the total charge that is carrying. It is not a neutral. It's not, no ion is a neutral. Of course, ion means it is carrying some charge, and the oxidation state for that element or that compound will be equal to the total charge it has. So it will be -8. -8 minus 1 is equal to -1, so that if we bring this -1 on this side, it will be -7, right? So what X has to be +7, only then the equation will equate, right? So from here we understand that manganese was +7 in this case. It is not magnesium, it is manganese. So it is not +2. Okay, my mistake, sorry. So manganese was +7 in the reactant side. So it is +7. And then on this side, it becomes +2. So the oxidation state increase or reduce? Oxidation state reduce. From 7, it goes down to 2. So reduction is happening here. Now we know that it is oxidation is happening here and reduction is happening for this case. So the oxidation reduction, I mean, we found out where the oxidation happening, where the reduction happening for sure. And then let's go to balance the equation. How we can balance the equation? There are two ways the reaction can happen. Again, one is in acidic medium, another is alkali medium or basic medium. For acidic medium, if it is an acidic medium, in acidic medium means acid means there are a lot of hydrogen ion because acid can give a lot of hydrogen ions, right? So acid means a lot of hydrogen ion. We do not have any deficiency of hydrogen in acidic medium. So there is, I mean, for manganate ion, there is manganese is forming. From manganate ion, manganese is forming. So what is happening for another, this 4 oxygen? I mean, forget about the charge now. At least there are 4 oxygen atoms involved here. What will happen to them? Oxygen is no, it's not oxygen gas is evolving here from this reaction. No oxygen gas is evolving. This oxygen will be converted to water. This is another rule that for oxidation reduction, convert the oxygen atom to water, not oxygen gas. Okay, we have to convert it to water, so that according to that rule, we are converting the oxygen to water, and from the 4 oxygen atom, there are 4 water molecule will be prepared, produced. To make this 4 water molecule, I need 8 hydrogen ion, right? I need at least 8 hydrogen atom to produce 4 molecules of water, because in one molecule of water there are 2 hydrogen atoms. So there are in 4 molecules of water there must be 8 hydrogens, right? And why 4 molecules of water? Because there are 4 oxygen atoms here. So by this way we can at least have some better picture now that what is happening here, that manganate ion is reduced to manganese ion 2 plus, and this 4 oxygen is produced to 4 water molecule, and 4 water molecule, each of them one molecule contain 2 hydrogen atoms, so 4 oxygen will take 8 hydrogen, and we have to show this 8 hydrogen. Don't be worried about where the hydrogen is coming from, how should I need to add anything. No, you are just telling us that it is in acidic medium. All right, it is an acidic medium, and that is all. That in acidic medium we know there are a lot of hydrogen, so that is it. Okay, so in the basic solution, hydrogen is concentration will be lower, and that is why hydroxide, we have to show the hydroxide. We will show it later, not now. In the next slide, I'm going to show what we'll do in the basic, to solve it in basic medium. So just remember, just like in acidic medium, we consider hydrogen ion, in basic medium, we consider hydroxide ion. That is okay. So oxidation reaction, iron is producing ferric. From ferrous, iron 2 is producing iron 3 or ferric. To producing iron 3, what is happening is it is releasing one. It is reducing one or releasing one electron, right? It is releasing one electron. Okay, it is releasing one electron from iron 2 plus. For iron 2 plus, it is going to iron 3. To go to iron 3, what we'll have to do is it has to release at least one electron, not at least, have to release one electron, and this electron is coming out from here. As I said, that for oxidation reaction, we have to make sure that the electrons are balanced. Of course, the elements are balanced, but electrons are balanced as well. So this manganate ion and hydrogen, these ions that is coming from the acid, and there are 5 electrons involved here. Before that, I need to forgot to tell you. Here we see that here was positive 7, right? Positive 7. Manganese was positive 7. It was negative 8. And in this case, manganese becomes positive 2. So, how many electrons did it has to take up so that it becomes positive 2? 5, right? 5 minus, 7 minus 5 is positive 2. Or in another way, 8 hydrogen ion, is having involved in 8 electrons, right? 8 electrons. Here it is 2 electrons, right? Here it is 1 electron. Forget about the charge on them, but here it is involved 1 electron. 1 here, this one. So 1 electron. And if we equate on the both sides, right? So it is 8 positive 1, 8 positive 1, 1 negative, and 2 positive as well. So altogether, if we bring these 2 on this side, so if we change the side for these two electron, it will convert to negative sign, right? It will convert to change the side. So it will, because there is a equal or arrow there. So we are changing the side and then it will become negative sign for these two electron if we bring this side. And if we bring this and equate it, it will become 8 minus 2 minus 1 is equal to 5 electrons, positive 5 electrons. So to make this reaction happen, we have to provide at least 5 electrons to this. At least 5 electrons to this, all right? To make this reaction happen. That means we see that there are 5 electrons is required for this reaction to occur. Otherwise, where this when this water is forming, where this hydrogen, where these electrons it is getting electrons that has been provided to it. And now these 5 electrons, we have to show that it is taking 5 electron and only then it is happening in this way. So these 5 electrons, since only iron is releasing electron and iron is the only one, it is releasing electron and the rest others are accepting the electron. So it is on iron, everything on iron to release the electron. So to find, but the problem is iron is only releasing only one electron, right? From 1 to 1, you see that only one electron. So what we can do is, if we multiply this reaction by 5, then I will get 5 electrons as well. And of course, there will be, here is 5, doesn't matter, but I will get it 5 as well. So that is our, our aim. So we multiply the iron is 5, and then I will get the 5 electrons here. It is 5 as well, doesn't matter. Doesn't matter, but our most important thing is interesting. Our aim is to get 5 electrons here. So we multiply by 5 all these things, and then this is as it is. I will keep it as it is. I don't need to change it, because if I just multiply by 5, I get 5 electrons, and that is all. I will get the reaction done. So yeah, and after that, just add on. So 5 iron, manganese oxide, manganate ion, hydrogen ion. There are 8 here and 5 electrons on both sides. 5 electrons in there as here, so it will be cancelled out from the both sides, and this is the reaction. This is the full overall reaction. So if it is asked you that show the reaction in the acidic medium, you will have to do in this way. In the basic condition, or in alkali medium, the reaction is mostly hydroxyl is involved. Hydroxyl is involved because base, it will give hydroxyl ion. So iron, we can previously, in the previous slide, iron was just shown as F2, positive charge. For this case, we may show it as the hydroxyl ion, because in basic medium, alkali medium, it will be mostly hydroxyl or ferric oxide or ferrosulfuric oxide, or ferrous oxide or ferric oxide in this way. So let's see in the basic medium, what will happen is, let's say the chlorine something, potassium chloride maybe, and potassium permanganate or something like that is reacted, sodium chloride probably, let's say it's reacted, and then is produced on the chlorate ion and manganese dioxide. Balancing it as an acid, if we consider this is an acid, then we have to, first of all, if even we do the reaction balancing in the alkali medium, still we consider as an acid, and then we multiply it with the hydroxyl ion, or add the hydroxyl ion on the both sides, so that it will be in basic. It's quite simple. The basic medium is, if we know how to solve the problem or equation in the acidic medium, the alkali medium is easy. So we have to, I mean, since again, there is oxygen is involved, right? And there is the difference between them. The oxygen is difference between them. What we'll do is the rest will make water. To make water, this is the rule. If there is an oxygen, balance the oxygen on the both sides by producing water. It doesn't, you don't have to consider that where the water will come from. Later on, you just add on hydrogen ion to make sure that the hydrogen and oxygen ratio is same in the reaction. All right. So if this is another rule that if, I mean, I just said before, now I'm saying it again. If there is oxygen, balance it with water or make it water to balance it. And then add on hydrogen. Doesn't matter it's an acid or base. In both cases, add hydrogen to make it water. And then on both sides, add hydroxyl ion. It's so easy. On both sides, we add hydroxyl ion. And since we are adding hydroxyl ion here and these two, hydrogen hydroxyl, will produce water. And on this side, we do not change hydrogen ion and hydroxyl ion. I mean, water and hydroxyl ion, we do not change. So it will be probably the water will be removed and hydroxyl ion will be removed on the both sides, right? Only water is removed. What here? The water is removed from the both side, so that the total reaction is at the end is reduced to this time, this as it is. All right. So this is a reaction that how do we balance the reaction in basic medium. We have seen the acidic medium and basic medium. Basic medium is the same thing. We have to solve it with the help of hydrogen ion first and then add hydroxyl ion. One thing you may, I mean, I was expecting a question that why the water is coming here. How do you put the water? This water is coming like here, right? So this water is from here. This is 2 molecules of water because it's 1 molecule of water is here and there's 2 molecules of water. So 1 molecule is cancelled out, another molecule is left over. You have to balance the water molecule as well and everything, hydrogen and oxygen as well. So now we understand the oxidation reduction reaction. We can understand the galvanic cell, voltaic cell. This voltaic cell, in fact, is based on the oxygen electron transfer, and that is why after some point this basic element that came at the beginning. There is a lifetime for these elements. All right, because of this we have a lifetime for these batteries. The battery finish up after some time. Because of this, the ion changes from year to year, day to day, month after month. So we are already, we know about the anode and cathode. So where oxidation happens, we call it anode. Where reduction happens, we call it cathode. So where oxidation is happening means which one is giving electrons or donating electrons. Anode will donate electrons. Anode plus E. Oh, sorry, not plus. Oh. Anode is donating electron plus E. Cathode is taking up electron plus E. All right, and then producing something else. So anode will give up electron or will donate, release electron. Cathode will take up. So just remember one is good enough. Just remember that anode is oxidation. NOx. Okay. NOx is a mnemonic you can consider. There is an ox. There is an ox. All right, so anode is oxidation. And this is the way that we write the shell, electrochemical shell. This is the way it's produced. So that it means that copper on half cell, there is a copper and copper ion is there, and another half cell is silver and silver, or another this anode, because this is the oxidation is happening. This is cathode, this reaction. This silver is taking up the electrons from here and is producing a silver solid. Okay, so this is it. Do you have any question? Anyone? Is there any question? No? If no question, then we'll take for another 5 minutes, I mean, just 5 minutes break, and then I'll start this acid and base again. And I promise it will be a simple thing, acid and base, that will start. Tomorrow, maybe we'll see something, and then next week we will see the buffer solution. So, or if you have any question now, you can just type in. I will come and see. I'm going to make some tea for myself. Okay, so I'll see you after maybe 5-7 minutes. All right.